Okay, hi again, students. So this is part 2 in chapter 7 as we focus more on standard error as well as finding or calculating z-scores with sample means in our distribution of sample means or sampling distribution of means. So let's begin with standard error. Again, as we've discussed in our previous part of this chapter, the standard error is the standard deviation of the distribution of sample means. Again, it reflects the discrepancy of sampling, which is called sampling error, because we're collecting samples from a population, and because we're not getting everybody and we tend to get values or scores that are closer to the sample mean but not exactly the mean, and whatever sample mean we get, as long as it's a sample and not the entire population, any sample mean would not be the same as the true population mean. Again, you could get the same value, but again, it's not the same. You're not using parameters, you're using sample statistics. Therefore, there is a sampling error when we use sampling. And so the amount of sampling error then varies across samples. Remember, in order to get a sampling distribution, we need more than one sample mean. In fact, we need all the possible sample means we can get. And when we work with large populations and when we work with sample size of 20, 30 or more, you're going to get lots and lots of samples. And that's why we have the central limit theorem, because we're going to do this with all the possible combinations, potentially infinite number of times. So with each sample mean, there is still going to be variability across the samples. And the variability across the sample means is this variability of sampling error. That is the standard deviation of the sample means, and that's what we call the standard error of the mean to reflect sampling error. So here, again, we are working with the sampling distribution with its own mean of means, and so on, and then it has its own standard error, which is the standard deviation of the distribution of sample means. Again, it's not the same as the standard deviation of the population distribution. However, the mean of the sampling distribution is the same as the population mean. So again, to remember, in the sampling distribution of means, the mean of that distribution is the same as the population mean, but the standard error is not the same as the population standard deviation. In fact, it's going to be smaller as n gets larger. So typically, assuming that the population that you use to get your sample is normally distributed and is large enough, often it's too large for you to just get the population, and assuming that your sample size is around 30 or more, then you're going to get a sampling distribution that is normally distributed and quite packed around the middle with a small standard error. So it would be normally distributed provided the conditions that we talked about. Again, the population is normally distributed and your sample size is large enough, like 30 or more. With that distribution, it has its own properties, its own mean of means, and its own standard deviation, which is the standard error. Again, here are some examples of how the standard error can change once you change the sample size. The smaller the sample size, the fatter or wider and flatter or shorter your sampling distribution is. Notice that all of these distributions are distributions of sample means. Notice you still apply the sampling technique. You still get up to infinite number of samples with this. But the change here, other things being equal, would be your sample size. So distribution A would have a sample size of 1 for each sample mean that is obtained. Distribution B would have a sample size of 4 for each sample mean that it's obtained for this distribution. And sample C would have a sample size of 100 for each sample mean that is obtained for the sampling distribution. So notice here that as the sample size gets larger, the standard error gets smaller. And if the sample size is 1, only then would your standard error be the same as the population standard deviation. I mean, think about it. Your sample size of 1, it just means, well, every person. That means all the scores. And that means you're just grabbing everybody. So it's not infinite in that case. It's just everybody. With anything more than 1, then you're looking at n approaches infinity because you're going to get more combinations that way. So there you go. Again, in sampling distributions, the standard error decreases as the sample size used to get your sample distribution, your sampling distribution of sample means gets larger. Notice, so here, as sample size goes up to 4, it gets taller, and the more scores, more sample means are piled up closer to the population mean. And finally, in a sample size of 100, you're going to get scores closer to the population mean in your samples, and the sample means themselves would also be closer to the population mean. Therefore, it's going to be really tall and skinny, where most of the sample means are going to pile up in the middle, close to the population mean. When you use standard error in research literature, you can write it as SE for standard error or SEM. Here, the M stands for the standard error of the mean, because again, this is the distribution of sample means. And SE just stands for standard error. Okay, because you are going to report a sampling distribution for you to make comparisons between population and sample, you would report the sampling distribution, including the sample size you use to get your sample, and which you'll also use to make a sampling distribution or to form one using the central limit theorem, and the mean of that sample mean, as well as your mean of sample means, as well as your standard error. So those will be reported when you do a research project. So for this class, you would be reporting it when you do hypothesis testing, and you would also report it in other classes if you do surveys or studies with samples where you would do a result and test your hypothesis using statistical procedures and hypothesis testing. You would report that as well, including standard error. So in this example, here you see, I got 2 samples, group A and group B. You want to see if these groups are different. So just by looking at it, you can go, okay, these groups looks different enough. And these are groups of means of scores. So here you can see, okay. If you got the means here, okay, at 15 and then these are plus or minus 1 standard deviations away, you can see there's no overlap between them, and therefore, okay, these groups look different. Again, if this was drawn in as a polygon, you can also see here that, okay, the standard error refers to the variability of sampling distributions. If you got two groups and you start to look at their means, and if you see, oh, okay, these distributions show no overlap, then you would say, yeah, they look different. But if you start seeing overlap, you would be less inclined to say, yeah, they're different groups, because the scores start to overlap one another and the means do as well. So before we forget, if you're wondering what the formula or how we calculate the standard error, we'll go through that right now. So, see here. So we'll take a moment to review this and use some foundations here that we learned from our previous chapters, like chapter 4. So remember, we calculated the standard deviation using sum of squares over n. For the population and for the sample, we use sum of squares over degrees of freedom, which is n minus 1. And the idea for variance is that, okay, I want to find deviation scores, and we know that we can't just use raw deviation scores because that's going to give us a sum of deviation scores of 0. So we need to start by squaring those deviation scores so we cancel out the negatives and dividing that by n. So then, okay, we get the expected, we start to get the expected deviation score. Standard deviation is the square root of the variance. Again, whether it's sample or population, population or sample, is the square root of the sum of squares divided by population size for population, or the sum of squares divided by your degrees of freedom, that's your sample size minus 1 for sample standard deviation. This is the formula that we're going to use for standard error. Notice here, because we already have calculated the standard deviation, or at least we would be given this information, whether it's by sample standard deviation or by the population standard deviation, which of the context of this course is given to us. So if we're given the population standard deviation, then we would get the standard error by dividing the population standard deviation by the square root of n, which is the same as, well, I'll be given the population variance and then dividing that by n. Here we're not using n minus 1 because we're working with the population standard deviation, which we know, and we don't need to account for sample bias per se, because again, we're working with sample means. And we need to take the actual n into account here because, well, that's the sample we use to get those means, the size of the sample. So again, if you see sigma over root n, that's the same as sigma squared over n, and then you square root all of that. So for example then, when we look at the standard error for these distributions back in slide 29, so here, let's say we've been given the population standard deviation of 20. And so for our standard error, we use the formula here. We could either use sigma over square root of n, or square root sigma squared divided by n. Here, well, we'll use the simpler one. 20 over square root of 1 is 20 over 1, which is 20. And you can check with the other way too. So 20 times 20 is 400. So you got your variance here. Again, it's 1. So, well, it's square root of 400, which is 20. So that's the same. So let's try standard error for something with a larger sample. So here we start with our population standard deviation, and we divide it by root 4 now, using the first way. Well, it's 20 over 2. Well, that's 10. Again, you can check with the other way. So it's 400 divided by 4. Well, that's square root 100, which is 10. And the last one, well, let's try it one more time. So again, we try to find the standard error, which is not the same as the population standard deviation when n is greater than 1. So let's try 100 in the denominator. So as you can see, that as the denominator, the n gets larger, your standard error gets smaller. So again, we start with the population standard deviation, that is 20, and we square root 100, which is 10. 20 divided by 10, that's 2. And then one more time, well, 400 over 100. Okay, let's square root of 4, which is 2. So it works. And we use n because we're working with the distribution of sample means, and the n actually counts here because, well, that's the size of the sample that we use. It's not the same as trying to get sample variance and sample standard deviation. This is the standard deviation of the distribution of sample means, not the standard deviation of a sample distribution. We don't need the degrees of freedom because under the central limit theorem, you're getting everyone. In sample size of 1, this is the most obvious. Yeah, you're getting everybody. So there's no need for n minus 1. That would be 0. You can't divide by 0. It's impossible. So again, because we are working with the sample to get the mean, we're not working with the sample distribution anymore, but it's a distribution of sample means. So we don't need n minus 1. We don't need degrees of freedom here. And the n here is used to reflect the sample bias, or the sampling error that we get once we get those sample means. So the sampling error is decreased because we're getting more values each time in larger samples that are closer to the mean. Again, if you get everyone in the sample of 4 in a population of 4, you can see you're going to get the mean every time. So this is what we're talking about. See? So back here, as sample size approaches the population and it's the same as the population, then your standard error is going to be 0 because you're going to get the mean every time. Whereas if you got a sample size of 1, that means, well, standard error will be exactly the same as the population because you're basically measuring the population at that point. So as you work with different sample sizes, you can do this with a smaller population. It's based on the whiteboard thing that I just showed you. You can see for yourself how standard error works, and you can see for yourself how you can apply the central limit theorem in sampling distributions using sample means. So now we go back. Looking ahead then to our next chapter, inferential statistics, where we start to test hypotheses and compare samples with populations first and then samples with other samples. We cannot make this comparison at all unless we can connect the sample data with the population data. Again, we are usually not given population data, And even if we are, we still need to find a way to compare the sample with the population. And a consistent way of doing that is using sampling distributions, because the sample size itself is going to change the way we approximate the population distribution using sampling distributions. So what we're going to do in hypothesis testing, the distribution we're going to use when we compare samples to population is not going to be sample and population, but the sample and the sampling distribution, which is the best estimate of the population distribution offered in this course. That way we can start drawing inferences and make conclusions about whether the sample is the same as the population, or whether a sample is going to be the same as the other sample, which in a way is saying whether the sample from which the population is drawn, or this population where you get your sample from, is the same population from the other sample. So that's going to be how you test sample to sample as well. So in this conceptualization, here's an example of this. You got a population of something, and it's normally distributed. We're going to assume this. And it's given a population mean and a population standard deviation. Here, now, we know, we have a sample. And of course, the sample, you have the sample mean, and then you also have some kind of sample standard deviation, in which you will use n-1, because, well, it's the sample distribution you're working with, not the sampling distribution. You could compare this sample with the population. You could compare this sample that is untreated with the population itself to see if it's from the same population. But the thing we're probably most interested in is, let's say there's some kind of treatment, something like, tutorials for courses, or vaccines for epidemics, or some sort of medication for some illness or something you want to fix. Could be like, I want to sleep more, or whatever. And so if there's a sample that received the treatment you want, and they're measured on something, it could be GPA, it could be a test score, it could be your health, like how many flus you're going to get, if it was like whether the vaccine works for flu, something like that. We want to see if it works. And so if we compare from one sample to another, well, you're really only comparing 50 people. But if you want to see if the sample here that's treated is going to be different from everybody else, again, you're going to need to compare at least the sample to the population. And again, if we can't get access to the population, we're going to compare that with the sampling distribution of means. Best approximation offered in this course that tells us, okay, this is what the population should look like. And that's next chapter. We're going to do this with z-scores. And so the z-score itself is going to be covered a lot more in the next chapter. Again, we'll be using skills we've already used, but the process itself is going to be covered in the next chapter. So the process itself, sampling distribution, can be used for anything, whether it's a group frequency distribution, or whether you're looking at untreated sample means and you compare it with treated sample means. What we're going to use in terms of hypothesis testing is going to be the application of this chapter, that is the sampling distribution of means. So let's finish off then with some learning check questions. Question 3. A random sample of 16 scores is obtained from a population with a population mean of 50 and the standard deviation, that is from the population, of 16. If the sample mean is 58, what is the z-score that corresponds to the sample mean? So remember the z-score formula for this. in this sampling distribution of means, or the distribution of sample means, then because we're working with the sampling distribution, we're looking for the mean, and we want to compare that in terms of the deviation score as the distance between the mean and the population mean, which we know. Oh, well, the mean of the sampling distribution is the same as the population mean. The interesting bit here is the standard error. So the process would go like this. Well, you know that the population mean is the same as the mean of means, so we know that's 50. That's the easy part. The standard error, what you're going to do next is, well, in this chapter, for this context, you're given both the population mean and the population standard deviation. So for this question, you're working with easy numbers. You got 16 as the population standard deviation, and here you got root n here is 16, so you put that in. So 16 divided by 4, so that's 4. So notice here again, your standard error of the mean, that is the standard deviation of the sampling distribution, is always going to be smaller than the population standard deviation when n is greater than 1. So you would not put in the denominator the population standard deviation. No, because that's not the distribution we're working with. We're working with the sampling distribution. Therefore, we put in the standard deviation of the sampling distribution. So here we go. We got the mean from the sample is 58. The population mean, which is the same as the mean of means, is 50. And then we divide it by the standard error, not the population standard deviation, which is 4. So it's 8 over 4. And the answer is 2. So the z-score then for 58, when the sample mean is 58, in the sampling distribution, it's going to be 2 standard deviations above 50. 2 standard deviations above the population mean, or the mean of means, in the sampling distribution. So again, this would be, you have your sampling distribution of means, and this is your mean of means, and then it has a standard error here, which we calculated as 4. So if this is 1 standard deviation, this would be 54, and then 2 standard deviations would be 58. And again, the values in this distribution are sample means, where n, and you would also note this here, it's 16. Again, you would want to show your reader what the sample size is in your sampling distribution, because the sample size here matters. Again, as sample size increases, standard error decreases. So here, yeah, the z-score for this question, when the sample mean is 58, the sample mean of 58 is 2 standard errors away from the population mean, or it's 2 standard deviations away from the population mean in the sampling distribution. Again, it's not in the population distribution, and it's definitely not in the sample distribution either. So 2 more questions. A sample mean of z-score with a z-score of 3 is fairly typical representative. It's a fairly typical representative sample. And you can take a moment and think about this. A sample mean that is 3 standard deviations above the population mean. Okay, that means the sample itself has scores that are close to 3 standard deviations away from the population mean in the sampling distribution. So the scores seem pretty high according to the question. So true or false for A. And for B, the mean of the sample is always equal to the population mean. Think about this one for a second, and when you read the question, make sure you know what distributions you're working with. Here it says the mean of the sample. So you can pause and write your answers if you want. So for the first one, there's a couple ways to think about this. First, notice it's the z-score. If you want a representative score, even in any distribution of scores, a z-score that is closest to 0, if not on 0, is going to be representative, because the z-score 0 means that, well, the value, whatever it is at the mean. The further the score is away from the z-score of 0 in a z distribution, the less typical and representative it is. In this case, in your sampling distribution, with its standard error. So you got 1 standard deviation, 2 standard deviations, 3 standard deviations. So this is z-score 3. And so the mean is somewhere here. So this is the sample mean we're looking at. And again, this is a distribution of means, where most of the means are going to pile up near the middle, about 1 or 2 standard deviations away. Well, 1 standard deviation above and below the mean. And as you go further and further away from the mean, you're going to get fewer and fewer sample means. So no, z-score 3 would be an extremely or unlikely z-score. The mean itself would also be not representative of the population. For B, the mean of the sample. Here is the mean of the sample. One sample, not sampling distribution. So the question itself would be false, or the statement itself would be false, because individual samples will always vary from the population. Which is why we need to do sampling distributions, where we get all the possible samples we can get and get the means from each of those samples, put them in a distribution to get the same value, where the mean of means is going to be the same as the population mean. So again, when we work with sampling distributions, we have several ways to tell. The first one is going to be standard error. Sometimes you'll see mu instead of mu or mean of means. But as soon as you can tell there's an M here, you're working with the distribution of means, therefore it's standard error. Sometimes they tell you what N is, which is useful. And so what we're going to do in the next chapter using z-scores, and you can try this now, and probabilities, is using this technique, we're going to find areas in which we decide, okay, if it's like 2 or 3 standard deviations away here, in this case it's 2 standard deviations away, which is like 95% of the entire distribution, and in this case 95% of the sampling distribution. Therefore, it's like 5% left, 2.5% on each tail here, if we do 2 tails. If we do 1 tail, where this is the entire area, it's still going to be 2.5 because, well, this is only 1/2 of this 95% right here. So we would say something like, oh, well, if the mean we get here is more extreme than this 64 in the sampling distribution, we would say, yeah, this particular mean right here, could be 65 or whatever, is not representative, not likely at all in comparison to the population mean in the sampling distribution of means, which is supposed to represent the population distribution. So notice here, yeah, this is where you're going to get your close to 2.5, and then this is where you're going to get your close to 95%. So here exactly, when you look at your unit normal table, the entire body here is going to be 97.72%, and then this tail here that represents your extreme positive mean values is going to be 2 and 2.28%. So those are the kind of questions we're going to ask next chapter when we start to look at hypothesis testing to see whether the sample mean or the sample is going to be different, comes from something that is different from the population. So that's it for today in terms of Chapter 7, where we looked at the distribution of sample means as a way for us to compare samples to populations. We have described the sampling distribution by its shape, its expected value, and its standard error. Again, this is the standard error that is the standard deviation of the sampling distribution. We've also described the location of a sample mean using z-scores. Again, the formula here is the same as the z-score for any score, but instead of using x and sigma, we use m for sample mean and sigma with a subscript m for standard error. So here it's sample mean minus population mean, which we know from a sampling distribution, that's the mean of means is the same as the population mean, and then we're measuring this deviation score in terms of standard error, not standard deviation of the population. And finally, because we're working with sampling distributions and we can transform those sample means into z-scores and we can use the unit normal table, we can determine probabilities, proportions within the sampling distribution for us to figure out where the sample mean is in that sampling distribution, and we can answer questions like whether that sample mean is a typical sample mean, whether that is representative of the population. So that's it again for today. You can use your resources to practice different sampling distributions. Again, I recommend working with small populations like 3, 4, or 5, so you can see the concept for yourself and try it. You can use the same small populations to figure out standard error, as well as the mean of means. And then you can start working with z-scores as you work with more common sampling distributions where, sample size is like 20, 30, or 16. And the practice questions you usually get with those tend to be values that you can square root. So it could be like 16, 25, 36, and so on. So again, you can practice using the textbook. You can practice using our web tutorials. And if you got any questions after doing those things, you can email me if you're studying at Alexander College. So again, that's it. You can do this and keep going. This is preparation for hypothesis testing, and we'll see you in the next one.